efficient. There's your solution, right? You got it. Now, but suppose you don't know this, right? Imagine yourself in a world where you don't know this. I want to show you how we can derive it using power series techniques. So this is the idea. Assume your solution has the form y is equal to sum n equals 0 to infinity of a sub n x to the n. By the way, guys, I've been using k as I've been using k as my go-to variable because I've been following the book. But honestly, my n's are much prettier, and so I'd rather do calculations with n. So that's why I'm doing n. It's just because I hate writing k, honestly. Anyway, so suppose your solution has that form. And so that's kind of like, it's a very flexible hypothesis, right? Because which functions are represented by power series? We had to work pretty hard to create a function which wasn't represented by a power series. Remember the bump function, problem 63? Like that's kind of a weirdo example, right? Typical examples that you come across in applications, in fact, do permit power series representations, continuous functions at least. Anyway, so that's a very flexible hypothesis. That includes a myriad of possibilities. Then you differentiate again, all right, term by term. Then what I do is if I want this to be a solution to the power series, to the differential equation, what do? You plug it in, right? So y prime prime plus y equals to 0 gives me that series plus this series equals to 0. Make sense? Because when you differentiate the first time, you lose the constant. When you differentiate the second time, you lose the linear term. So it starts at quadratic. Yeah. The differentiation shifts the powers. But that said, we want to add these together, right? But you can't add apples and oranges, right? But you can add apples to apples, I guess. I don't know. Whatever. It's a saying we have. The point is, I need to reformat these so that they match, so that we can add them. So the way to do that, in my opinion, I mean, there's lots of ways, but here's a way. Just make n minus 2 equal to j, and make this one equal to j, so then they'll match up. I've showed you this idea at previous lecture, right? Anyway, here it is again. So if j is equal to n minus 2, that means n is equal to j plus 2. So j starts at 0 because n started at 2, goes to infinity. N becomes j plus 2. N minus 1 becomes j plus 1, right? And then you have a sub j plus 2, x to the power j, and over here a sub j x to the, this one's easier, a j x j. Okay, now I can combine them into a single series. That single series is equal to 0. This is an identity for all x. That forces every one of these stupid coefficients to be 0 for each j, for j equals to 0, 1, 2, 3, 4, 5, 6, Trump's net wealth. Rounded up to the next integer. All right, so anyway, the point is that this is true for all values. So what that means is you can solve that for this precious recurrence relation, right? What's a recurrence relation? Well, we talked about those a little bit before, remember? We defined the factorial in terms of a recurrence relation, but this is a recurrence relation. So how do you solve recurrence relations? I mean, roughly speaking, the answer is one step at a time. What I do is I plug numbers into them and try to recognize a pattern. So like this one, if you plug j equals 0, you get what? You get a sub 2 is minus 1 over 2 times 1. This number is always the same as that number. See the pattern? And that number is always 1 less than this number. That's the pattern here. So a sub 2 is minus 1 over 2 times 1, a sub naught. A sub 4 is minus 1 over 4 times 3 times a sub 2. But we already know that a sub 2 is written in the terms of a sub naught in the step above, right? So that's minus 1 squared over 4 times 3 times 2 a sub naught. Aha! 4 times 3 times 2. Well, this is minus 1 squared over 4 factorial a sub naught. Yeah. And then, again, a sub 6 minus 1 over 6 times 5 times a sub 4. But a sub 4 is got a 4 factorial and a minus 1 squared, so I get minus 1 cubed times 6 factorial. You keep doing this until the pattern hits you, right? And if you search your heart, you can see that, in fact, the pattern for even coefficients is every even coefficient can be re-expressed in terms of the 0th coefficient times minus 1 to the k over 2k factorial. What happens if we look at the odd coefficients? Oh, come on. We have a sub 3 minus 1 over 3 times 2, a sub 1, right? A sub 5 minus 1 over 5 times 4, a sub 3, which is minus 1 squared over 5 times 4 times 3 times 2, aka, well, there's also an a sub 1 here, right? Minus 1 squared, a sub 1 over 5 factorial. A sub 7 minus 1 over 7 times 6, a sub 5, which, by the way, is minus 1 cubed over 7 factorial, a sub 1, and so forth, right? You can see the pattern. A sub 2k plus 1 is equal to minus 1 to the k divided by 2k plus 1 factorial, a sub 1. There's no guessing involved here, really, except for the initial step, which was to suppose that the solution has the form of a Maclaurin expansion, right? Which, again, is a totally reasonable guess, since what can you make it a Maclaurin expansion? Well, like pretty much anything, right? Totally reasonable guess. And so, drawing the conclusion together here, and putting the summarize, what we found is that y is equal to a sub 0 times that series plus a sub 1 times that series. You know them, you love them, cosine and sine. And so we just used a power series technique to derive what I pulled from the thin blue sky earlier in the course. Now, when I teach differential equations, if they'll let me, I mean, they let me sometimes. You know, what we do in there is I go over first, I mean, we go over various hodgepodge of techniques for solving first-order problems. You've seen 2/3 of that in here. The thing we haven't covered is what's called exact equations, all right? So you have that to learn. And there's some substitutions that are complicated. And then we go on and we look at these kinds of problems, constant coefficient techniques. Basically, if you understand the second-order case, you can do those. You've seen about 40%, maybe 50% of that story. The other part of the story is how to solve, like, what do you do? Like, I have not showed you guys anything about how to solve something like, if you've got a t squared here or something, what on earth do you do with that? Well, I guess in our current language, x squared. You know, how would you solve something like that? We haven't talked about that. When I taught Calculus 2 at NC State, that was part of the course in Calculus 2. All right? So, but anyway, getting back on track. Of course, we haven't done that, and I won't do that unless you take differential equations. So great. You know, there's this standard kind of trickery that you do. And you learn a few other substitutions. After all of that is done, you study power series solution techniques. Right? So basically, what I've just showed you is what we show you in differential equations. That's just the same. It's no different than what I just did. This also comes up in DiffEQ. We do this about maybe 2/3 of the way through the semester, something like that. But the thing about this technique is it kind of picks up the pieces. It takes care of examples which are not amenable to nice algebraic solutions. And something more, this technique even solves weird problems like this one. Like, I can go through the same idea I just went through with putting like an x squared here or something. I will get a different recurrence relation, and I will derive power series solutions to that differential equation. just the same. Past that point in diffie-q, there's something called the Frobenius method I mentioned earlier today, something called regular singular points, and there you have things that are not power series solutions, and that's a subtle and deep business that's best left to differential equations. I mean, in a given semester, we may or may not cover Frobenius method, because it's difficult. But it's never really much different than this. If you understand this, this is a big chunk of like the harder part of diffie-q. When people take differential equations, you know why they have trouble? Because they never learn this. I mean, what they never really learned was differentiation, right? But by the time sometimes people take differential equations, their series calculations have kind of got rusty. They've forgotten about these things, right? And that's unfortunate. But anyway, that won't be you guys. Because some of you are not taking differential equations, right? No, I'm just kidding. That wasn't really my point. Yeah? Yes, sir. Oh, no. Any questions? So just to give you what we're doing, tomorrow is assessment day. I don't think I'll have office hours at 7 tomorrow, if that's okay with you guys. I will probably have office hours at some point. I need to find out like what I'm doing for the department or not doing, and if I can find a good time, I'll announce it. If not, you can just try to hunt me. Anyway, I'll have office hours Thursday, of course. And Thursday, we'll also have the whole time just for questions you guys have about section 12.9. I'm actually not going to ask another in-class quiz because I don't have time in my schedule to grade quizzes. I have to admit it. I will hopefully have your quizzes graded and turned back to you Thursday. And I'll also hopefully give you a quiz that you can work on and we can discuss, all right? But not graded. I would encourage you to look at old tests, like old test 4, give you a sample of like typical power series calculation examples that I've put on tests back in the day. Of course, your test will reflect this current semester, right? And then Friday, probably I'll cover the first section in chapter 10, which will not be on the test. It's just that we're running out of class time past this next test, and I need to like try to do something to try to not make it too compact. And I think we'll be okay for series if we set aside Friday for the chapter 10. Monday, we will have for questions, whatever questions remain about the material, and then Tuesday will be the test. So that's the structure going forward. I'll shut up. Anyway, thanks, guys.
What's
that?
Are there